Hello, everyone. Welcome to Brain Blitz Audios. Today, in this episode of NEET Preparation, we'll be looking at previous year questions of chemistry and medical entrance examinations in India. Today, we'll be dealing with the chapter, the P block elements. Now, this is the seventh chapter in the grade 12 syllabus for chemistry in CBSE. We'll be looking at group 15, 16, 17, and 18 elements in this chapter. This is a continuation of the same chapter of the same name in grade 11. Let's move on to our first question. Choose the correct statement. White or yellow phosphorus is stored underwater. Ignition temperature of red phosphorus is low. Black phosphorus is non-crystalline in nature. And phosphorus does not form hydrides. We need to find out which of these is the correct statement. Let's start from the bottom. Statement number D. Phosphorus does not form hydrides. Well, phosphorus does form hydrides, so therefore this option will become downright incorrect. An example for a hydride from phosphorus is pH3, which is also known as phosphine. So option D is incorrect. What about option C? Black phosphorus is non-crystalline in nature. Well, this statement is also incorrect. Black phosphorus is crystalline. It has a crystalline structure. What about option B? Ignition temperature of red phosphorus is low. Well, if that's the case, then red phosphorus would catch fire easily, but that does not happen. So option B is incorrect. Ignition temperature for red phosphorus is very high. Therefore, the right statement is option A. White or yellow phosphorus is stored underwater. Now, this is due to the low ignition temperature. Now, white phosphorus has a low ignition temperature, so it undergoes oxidation in the air, which means that it catches fire spontaneously. If you keep it in air, it's going to catch fire, so it is stored underwater. That's why option A is the right option. Next question. An element X forms compounds of the formula XCl3, X2O5, and Ca3X2, but does not form XCl5. Which of the following is the element? We have boron, aluminum, nitrogen, and phosphorus. Now, boron and aluminum belong to group 13, and these are metals. However, since they are metals, these two elements do not form Ca3X2. So therefore, options A and B are incorrect because these two options do not follow the first condition of forming Ca3X2. So options A and B are incorrect. So now we have nitrogen and phosphorus left. If we look at phosphorus, yes, we do have Ca3P2, we have PCl3, and we have P2O5, but we also have PCl5. Phosphorus is a maximum oxidation state of +5, which means that phosphorus can form XCl5. So that means option D is incorrect. The right answer is option C, nitrogen, and this is due to the absence of d orbitals. When there is an absence in d orbitals, the highest oxidation state that you'll get is 3. So it has maximum covalency of 3. So that you cannot form NCl5, whereas you can form PCl5. So option C, and nitrogen is the element which does not form XCl5, but can form XCl3, X2O5, and Ca3X2. So option C is the right option. Next question. H2S gas is not evolved when SO32- ion reacts with which of the following reagents? Over here, the right answer is option B, Al plus concentrated NaOH. Here's the reaction. SO32- is our ion plus 2Al plus 2OH- because this is an ionic reaction, plus 3H2O. And this forms S2- plus 2 in, and then the coordination compound AlOH4-. So we have S2 minus, and it reacts with hydrogen to form H2S. But this H2S is neutralized instantly by the NaOH present. So it becomes Na2S. So therefore, there is no evolution of H2S gas. Even though it's formed, it does not evolve because it instantly gets converted into Na2S. That's why option B is the right option. Next question. In the nitrogen family, the nitrogen family element and then hydrogen bond angle in the hydrides MH3 gradually becomes closer to 90 degrees on going from nitrogen to antimony. This shows that gradually A, the basic strength increases, B, almost pure p orbitals are used, C, the bond energy increases, D, the bond pairs of electrons become nearer to the central atom. Which of these is the right option? Well, if we look at option D, bond pairs of electrons become nearer to the central atom, well, this option is incorrect. Now, the condition bond pair of electron become nearer to central atom is the explanation for electronegativity. And when it comes to electronegativity, nitrogen is the highest. So it is the most electronegative. So option D is incorrect. Option C, bond energies of MH bond increases. Once again, NH bond is the highest in terms of bond energy. So option C is incorrect. Option A, the basic strength of hydrides. Yes, that increases, but this has no role in determining the bond angle. The bond angle does not depend on the basic strength of hydrides given directly. So option A is incorrect. The right answer is option B. Almost pure p orbitals are used for MH bonding. Now, the reason for this is when we form hydrides of group 15, they are usually in the tetrahedral shape with 3 hydrogen atoms and a lone pair. Now, for nitrogen, from nitrogen to antimony, the lone pair of the central atom becomes more dispersed. So that means there is less repulsion, so bond angle nears 90 degrees. And for lone pairs to become more dispersed, we have to use pure p orbitals. And that's why option B is the right option. Let's look at this question. Which of the following oxides is the most acidic? We have 4 oxides given, so the first thing we need to determine is the oxidation state. For Ag2O, oxygen always has 2 minus as its oxidation state. So therefore, 2 times of +1 will be equal to 2 minus of oxygen. So for silver, it is +1. For vanadium, O5, so 5 into 2 minus, so that is 10 minus totally. So we will have 2 times of 5 plus in order to counteract 10 minus. So vanadium has an oxidation state of +5. Carbon has an oxidation state of +2 in order to counteract -2 of oxygen. And similar to V2O5, in N2O5, nitrogen also has an oxidation state of +5. So, which of these is most acidic? Well, vanadium and nitrogen both have the same oxidation state. So therefore, both of these are larger, are more acidic than Ag2O and carbon monoxide. However, between vanadium and nitrogen, you will notice that in the periodic table, nitrogen is in a position where there is more electronegativity. So nitrogen is more electronegative because it is to the right of the periodic table, while vanadium is to the left. And moreover, vanadium is actually 2 periods lower than nitrogen. So therefore, the electronegativity also differs greatly. So nitrogen is more electronegative than vanadium. And when it comes to oxides being acidic, electronegativity also matters. So the more electronegative the central atom is, the more acidic it gets. That's why option D, N2O5, is the right option. CO and Ag2O have different oxidation states, and vanadium is less electronegative, which is why dinitrogen pentoxide is the most acidic oxide among the following. Let's see this question. When chlorine water is added to a solution of KBr, the solution immediately turns orange-red because chlorine is reduced to chloride ion, formation of BrCl. Bromide ion is oxidized to bromine, of the formation of Br3 minus. So let's write down what happens when chlorine water reacts with bromine. So chlorine water plus Br2, this gives you 2BrCl. Chlorine water plus KBr, this gives you bromine. And when bromine reacts with chlorine in water, you will get 2BrCl. Now, when we look at this process, we notice that chlorine is reduced to chloride ion in the final product, BrCl. And we also notice that the bromide ion in KBr becomes oxidized to Br2, bromine. And we also notice that there is a formation of BrCl2. But there is no formation of Br3 minus. So option D is incorrect. Now, we notice that the solution immediately turns orange-red. Why does it turn orange-red? Because BrCl2 has the color orange to red. So an orange-red color is due to the formation of BrCl2. Option B is the right option. Now, both A and C occur. These are not the reason for the change in color. The change in color is due to the new product, which is BrCl, which is a hydrogen halide, and hydrogen halides are usually colorful. Next question. Which of the following halides is the most stable? Now, when it comes to stability of carbon halides, so all of these are carbon halides. So when it comes to carbon tetrahalides, then the rule of thumb is that stability decreases with increase in the size of halogens. So what happens is that as the halogen size increases, the stability of the carbon tetrahalide decreases. So which of the halogens is having the highest size of atom? That is iodine. So Ci4 will be least stable. CBr4 will be more stable because bromine is smaller. By that rule, CCl4 will be more stable because chlorine is even smaller, but they are dwarfed by the stability of CF4, carbon tetrafluoride. This is the most stable of the carbon tetrahalides. So CF4, option C, is the most stable of the following carbon tetrahalides. Option C is the right option. Let's look at this question. Noble gases are absorbed by anhydrous calcium chloride, ferric hydroxide, concentrated H2SO4, activated charcoal. Now, when it comes to absorption, usually this is undertaken by an absorbing agent. But when we study calcium carbonate, calcium chloride, ferric hydroxide, and concentrated H2SO4, all of these are dehydrating agents. So they are primarily dehydrating agents, so they're not good at absorbing noble gases. So options A, B, C are incorrect. That leaves with option D, activated charcoal, which is a very good absorbing agent. So that's why option D, activated charcoal, is used to absorb noble gases because it is a good absorbing agent, while the other options given are dehydrating agents. Let's look at this question. Which one of the following is the correct decreasing order of the boiling point of group 16 hydrides? So the hydrides given belong to group 16. Now, when it comes to group 16 hydrides, there are a couple of things that you need to look at. Firstly, the boiling point of H2O is way greater than the boiling point of H2S. And that is because of intermolecular hydrogen bonding. So when we look at ice, we know that each of the water molecules, they have hydrogen bonds with the other molecule, and that's why they form a lattice structure. The same reason why ice is less dense than water is because of the intermolecular hydrogen bonding. So that is one thing. What is the other? The second thing is that H2S has lesser boiling point than H2SE, which has lesser boiling point than H2TE. And this is due to the increase in atomic size. Now, how do we exactly know which is the right order? Have a look. This is a graph between the boiling point and the molecular mass of hydride. As you can see, hydrogen has one of the highest of the boiling points. It's almost 100 degrees Celsius, that is 273 degrees Kelvin. 373 degrees Kelvin, so it is pretty high. And as you can see, for H2S, it's extremely low, it's sub-zero. So therefore, H2S will be the lowest. And then H2SC is increased because of the increased atomic size, and H2TE becomes even more because of the increased atomic size. But none of these are comparable to H2O, and that is due to the intermolecular hydrogen bonding. So therefore, option D, H2O greater than H2TE greater than H2SC greater than H2S, is the correct decreasing order of boiling point. Option A states that H2TE is more, and that would be true if this followed the general order of increase in atomic size. But since H2O has intermolecular hydrogen bonding, option A is incorrect. Option B states that H2S is more. However, H2S in the graph is given as the least, so option B is incorrect. And in option C, this would have been the correct order if we followed the increase in atomic size model. However, that is incorrect because we know that oxygen has intermolecular hydrogen bonding. So therefore, the right answer is option D. Boiling point of water is greater than tellurium, greater than H2SE, and which is all of which are greater than H2S, hydrogen, sulfur. This is our final question. Total number of lone pair of electrons in XeOF4. So XeOF4 as an octahedral structure. Let's draw it one by one. So in the middle, there will be a xenon atom, and it has a perfect octet. So it should have 8 electrons outside in the outermost shell. So in the outermost shell, xenon has 8 electrons. Now, fluorine has a single bond with xenon, and that bond occurs in the same plane. So as you can see, we have this structure. Now, that is due to the oxidation state of fluorine being -1, so it only needs 1 electron. So it borrows 1 from xenon. So basically, we have 4 of these borrowing together. But why not 8, for example? We have an oxygen coming in between. And this oxygen has an electronegative, has a valency of -2, so it takes 2 electrons. And finally, that leaves 1 lone pair of electrons in the structure. Since there's only 1 lone pair left, option B, which is 1, is the right option. Option A, option C, and option D are incorrect, because the right amount of lone pairs by drawing a structure of xenon is just 1. So there's only 1 lone pair in the structure of X2O5. And that's why option B is the right option. That concludes this webisode of NEET preparation. We've uploaded many videos of the chapter key block elements. Don't forget to look at the playlist, whose link is given in the description down below, and you'll be provided with a lot of videos which concur with NEET preparation. And if you want to get more of our useful and interesting content, then don't forget to subscribe to our channel. It's Brain Blitz Audios. And therefore, until the next episode, take care, stay safe, bye-bye for now.